Hello and very good morning to all. We will like to present our assignment, a foil wing assignment, KIG2003 Fluid Mechanic 2. Our team name is Pre-Syar and our lecturer is Prof. Abdul Kalam. This is our list member and their metric number. So introduction and literature. The Wright brothers invented and flew the first airplane in 1903, recognized as the first sustained and controlled heavier than air powered flight. Airplane comes in variety of size, shape, and wing configuration. The aircraft mostly have a flexible wing surface to provide lift when flight. The wings are designed by following the Bernoulli's principle, which provide the necessary forces the aircraft needed to fly. Thrust, drag, lift, and weight are the type of forces that act upon all aircraft in flight.
I'm Pre-Syar, metric number U20033951. I'll be talking about our proposed conceptual design. So we have multiple aspects as to why we designed our wing the way we did. So there's 4 cross-section shapes, angle of attacks, area or size of the wing, and trailing edge. So according to the Bernoulli's principle, a fluid that travels at a higher velocity generates lower pressure. So based on this theory, the streamlined shape of our model is aerodynamically designed so that the wind travels faster over the airfoil and then slower below the airfoil. So the pressure difference between the top and the bottom generates the net lift of the airfoil. So the bigger the pressure difference in between the top and the bottom region, the higher the lift force that will be generated. So in order to maximize this effect, we deliberately designed so that the top of our wing will have a bigger curvature compared to the bottom, while the bottom is almost flat, so that we can easily achieve a higher lift force due to bigger pressure difference generated even at a lower angle of attack. So the purpose of making the airfoil achieve a higher lifting force even at a lower angle of attack is to minimize the drag force that is generated by the friction between the surface of the airfoil and the wind. So drag force exists perpendicularly to the lift force and is perpendicularly to the lift force, so it's like this, and in parallel to the wind flow. So as we can see on the formula given, the drag force is influenced by the area. So in order to minimize the drag force, a lesser area of contact is required between the wind and the wing. Hence is why we opted to design an airfoil model that could achieve high lift force even at lower angle of attack. So as for the area of the wing, this project sets the span limit of the wing for 100 mm. Since the lifting force is directly proportional to the area of the wing, we picked the maximum possible span allowed for the project, which is 100 mm, and the chord is about 40 mm. We did so to obtain the highest possible size of area. So the bigger the planform area would require the air to travel larger area of it and would result in lower pressure region over the upper region, which in result contributes to the increase of the overall lifting force of the wing. Lastly, for the trailing edge, we opted the design for this trailing edge of this wing so that it is as sharpened as possible, which can be seen on the picture given. So it would be easier for the higher air pressure to bleed it because from the bottom region to bleed into the upper surface region of the wing, resulting in a reduce in the net lift force if the trailing edge if it was designed to be circular. So since we did design it to be a sharp edge, we can avoid that predicament by making the air have a hard time to go around the sharp edge. Hence, we can say that the design choices we made would result in an optimally lifting force generating wing with minimum drag force.
As for the methodology part, we are measuring the lift and drag force generated by our airfoil model. There are several steps to carry out the experiment. Firstly, the airfoils are attached and tightened to the hinge of the wing holder, where the angle is set at 0 degree. The initial and lift mass from the wing balance and Arduino setup are recorded as control data. The RPM knob is adjusted to set the velocity of the wind at 5, 7.5, and 10 meter per second. The velocity of the wind is measured using mini anemometer. The value for drag and lift mass was recorded for each different velocity. And lastly, the experiment is repeated with 4 different angles: 5 degree, 10 degree, 15 degree, and 20 degree.
Alright, so moving on the result part. So the data collected is tabulated into 3 different tables, which is the first one is for velocity equal to 5 meter per second. For the drag force, the highest value collected is on 0.126, which is at angle of attack 20 degree. For the lift force, the highest value collected is 0.153, which at angle of attack 15 degree. For velocity equal to 7.5 meter per second, the highest drag force is at 0.150, which is at angle of attack 20 degree, while for the highest lift force, it is at 0.181 Newton, which is at angle of degree 15 degree. For velocity equal to 10 meter per second, the highest drag force collected is 0.228, which at angle of attack also at 20 degree, while for lift force, the highest value collected is 0.259 Newton, which is also at angle of attack 15 degree. So the graph for angle of attack versus lift force and drag force are tabulated, which is this one is for 5 meter per second. So the lighter green represent the lift force, while the darker green represent the drag force. As we can see from the graph, the highest value for lift force is somewhere around 15 degree, which as you can see in the table, while for the drag force, the highest value is somewhere around 20 degree angle. For the graph for angle of attack versus lift force and drag force for 7.5 meter per second, we can observe the same pattern that is occurring, which the highest lift force occur around somewhere 15 degree, and the highest drag force is occurring around 20 degree angle. From the data, we can observe that around 50 degree angle is the critical angle, as the lift force is maximum at somewhere around 15 degree, and anything above angle of attack more than 50 degree is the stall, which will be explained more on the discussion part. Now for graph for angle of attack versus lift force and drag force for 10 meter per second, as we can observe, the lift force doesn't really follow the same pattern as two graphs before. This is due to some error in experimental setup. This will be explained more on the problem and challenges section later. Now for the discussion part. The highest lift force obtained is 0.244 Newton, which is at 15 degree angle of attack with velocity equal to 10 meter per second. The result obtained can be explained by the concept of aerodynamic lift and drag, in which the lift and drag force are influenced by the angle of attack. Essentially, the lift force are the most crucial part because that is the force that responsible for making the wing upward. So at low angle of attack, the flow of air across the wing is laminar with minimal amount of turbulence present at the trailing edge of the aerofoil. The angle of attack will gradually increase the lift force until it reaches the critical angle. So what if critical angle of attack? Critical angle is defined as the angle of attack that produces the maximum lift coefficient, and if the wing thrust tilted to an angle above the critical angle, then the lift force will be reduced as the air begins to flow less smoothly over the upper surface of the airfoil and begins to separate from the upper surface. So based on the result we obtained just now, we can observe that the critical angle is somewhere around 15 degree due to the fact that most of the maximum lift force occurs somewhere around 15 degree for the three graphs that we made just now. And from the three graphs we made just now, we can also observe that after 15 degree, the lift force start reducing due to the fact that it is already exceeds the critical angle and is become into the stall phase. I mean the wing is at the stall phase, which will be explained later. So typically the maximum angle of attack is ranged from 15 degree to 20 degree. However, this vary based on the type of the wing. So for our wing, the critical angle is at 15 degree. Now moving forward on stall, which was mentioned just now. So the lift force is reduced after it reached critical angle. This phenomenon is called as stall, in which the angle of attack has reached the stall angle. Stall can be defined as a sudden reduction in the lift generated by an aerofoil when the critical angle of attack is reached or exceeded. This angle fluctuates relatively little in response to the aerofoil's cross-section and is normally around 15 degrees, which is the case for our result. Now moving on the improvement that can be implemented on our wings. First off, we can add flap to the trailing edge, and also we can add slats to the leading edge. So regarding the flap and slats, both of them actually have a same function, which is to increase the angle of attack so that the wing can reach its maximum lift force with a lower velocity. This is helpful for an aeroplane during takeoff. The only difference between flap and slat is that flap is an extension on the back edge of the wing, while slats is an extension on front edge of the wing. Now another improvement that we can implement on our wing is that we can add winglet at the wing tip. Winglet is a vertical extension at the tip of the wing, as it can reduce the drag produced by the vortices near the tip area.
Hello, my name is Hazim, and I'll be explaining about the problems and challenges faced during this experiment. So as can be seen, there are four problems and challenges. So I will explain for the first one, which is regarding about the pivot of the wing holder that is not overlapping the center of protractor. So obviously this is wrong because if the center of the pivot is not aligned with the center of the protractor, it will give wrong angles. If the angle that can be seen from the protractor is 20 degrees, it is not exactly 20 degrees for the actual wing angle. It's going to be more than that because it's located slightly higher, as can be seen in the diagram inside the report for this experiment. So in order to solve this, the center of the pivot for the wing angle holder should be adjusted so that it's exactly overlaps the center of the protractor. But this cannot be done inside this experiment due to complexity issues to move the center of the pivot. So we continue with the center of pivot being slightly higher. Next is the weak structure of the wing holder. The wing holder can be said as flimsy because at high wind velocities it starts to wobble. So it's going to give the structure unnecessary movements, so it will move maybe slightly to the right or left, front, or even back. So that will obviously mess with the results that is going to be obtained, especially for the drag force. So it cannot be seen at low velocities, but when the velocity for the wind velocity increases at higher velocities, the holder starts to wobble. So in order to solve this, the structure of the wing holder should be increased in weight so that more force is required to wobble it. But it will not mess with the results for the drag force because it will only require more force to wobble it, not to give higher drag force. And thirdly, the adjustment for the wing pivot cannot be adjusted to an ideal tightness. This is because also, at high wind velocities, the angle of the wing holder starts to change. This is because the force from the wind pushes the wing to a different angle during the experiment. So obviously this cannot be accepted because for one trial, if the angle is set to, for example, 20 degrees, it should be 20 degrees all along the trial. So in this case, when the angle is set to 20 degrees, at high wind velocities, it will start to change to higher angles because it's being pushed by the wind. So in order to solve this, the tightness of the wing holder should be adjusted to an ideal tightness. But obviously this cannot be done from the structure, which is also a setback for our structure. And so I'm moving on to the last problem and challenge that we faced is the Arduino sensor that was used in this experiment is not that accurate. This is because even small movements from the wing holder structure gave very significant different readings at the Arduino sensor. Obviously, the Arduino platform can be used to obtain experimental data, but it's not that reliable. So because certain Arduino sensors, to give an example, have only they are limited to um, certain intervals to display the data. For example, 0.02, so it cannot be that accurate. So in order to solve this, a suggestion that we can give is to replace the sensor with a high quality sensor that can give more accurate readings, so that the overall results will be as accurate as possible. So those are the challenges and problems that we faced during this experiment. So I will now move on to the next slide. Thank you. Here are our list of references that were used throughout the experiment. So that is all for this presentation. Thank you very much.